Let's do a problem where we cannot exploit symmetries. So I have sort of an x, y axes because, yeah, why not? I have a finite line of charge here. We'll make this y sub max. And then I have a point over here at some point x0. What is the electric field at this particular point? This has some charge, total charge of Q. I did not tell you whether Q is positive or negative, and so we assume it's positive. The electric field should be, well, at that point it's pointing in that direction, that point's pointing in that direction, so it should be somewhere in between. This is slightly closer than that is, and so it should be something along those lines right there. We do not have the symmetries to exploit, and so it's a little bit more math, but very doable. So what I'm going to do is I'm creating some dq here. I'm creating the angles that I need. So my electric field from dq is pointing in that direction right there. And I'm going to make that x sub m. So x sub m, and that's y is equal to 0 there. All right, so the electric field. So I start out with a differential. That's equal to k. And again, for those who don't like writing k, I've had some students who really want to use the 1 over 4 pi epsilon sub 0, and that's fine. I just write k because it's less pen strokes. Saving ink, saving the world, a little bit of plastic at a time. I'm assuming the ink is carbon-based. Oh well. So k dq over r squared. And then we do have components here. It is going to the right if I go into, again, I and j hat like that. Then the cosine theta I hat minus sine theta j hat. Distribute, so I have k dq over r squared. So that is r right there. Cosine theta I hat minus k dq over r squared sine theta j hat. The distance from here to here is y. So I basically have a triangle here. I have y this way, I have x sub m that way, and then I have r that way. It is a right triangle. So let's solve for this one first. So I have k uniform density here, so let's go ahead and let lambda equal q over y sub m, so the charge divided by the length, or dq over dy. dq is equal to lambda dy, and that's a substitution what we will make. So I have k lambda dy over r squared. I'm going to hold off on that substitution. We'll use Pythagorean theorem. I know r squared is equal to y squared plus xm squared. Cosine of theta is the adjacent over the hypotenuse, and so that's x sub m over r. There's my cosine of theta I hat. While we're here, so this becomes k lambda dy over r squared, and then sine of theta is y over r j hat. We do get two very common integrals that we will just absolutely enjoy doing. So my electric field is k lambda x sub m, those are my constants, I hat, times the integral of, what am I left with? I have a dy over r cubed minus k lambda j hat, integral of y dy over r cubed. I know r squared is y squared plus x sub m squared. This becomes k lambda x sub m I hat times the integral of dy over y squared plus x sub m squared to the 3 halves minus k lambda j hat integral y dy over y squared plus x sub m squared to the 3 halves. This we can use U substitution for, like I've done in another video, and this one we need to be able to look up or to be able to do from scratch. And I'm not going to do it from scratch because I've done this enough times. The limits of integration, we go back to our drawing right here. It goes from 0 to y sub m. That's the smallest value to the largest value here. So 0 to y sub m, 0 to y sub m. Since y is my variable, this becomes k lambda x sub m I hat times y over x sub m squared, square root of y squared plus x sub m squared from 0 to ym minus k lambda j hat, well, u substitution, so u is equal to y squared plus x sub m squared, du is equal to 2y dy. There's my y dy, so divide by half, so over 2, integral du over u to the 3 halves. That's u to the negative 3 halves du. So add 1, so that becomes u to the negative 1 half, divide by that new exponent, and there we go. So that is equal to negative 2u to the negative 1 half. So this, which is negative 2 over the square root of u, and u is equal to that. So we end up with k lambda x sub m I hat y over, oh, and bring that x sub m out. That will cancel out there, and I'm left with x sub m here. Square root of y squared plus x sub m squared, 0 to y sub m, minus k lambda j hat over 2. Actually, that 2 is going to cancel out with that 2 right there. And the negatives will cancel out. And so I'm left with 1 over the square root of y squared plus x sub m squared from 0 to y sub m. Plugging in y sub m here, so I get k, well, let's just stick the I hat first, times k lambda over x sub m, y to the m over the square root of y m squared plus x m squared minus 0. Plug 0 in for y, get 0 over x sub m, plus k lambda, I'll stick the j hat first, k lambda, plug the y m here, we get 1 over the square root of y sub m squared plus x sub m squared, minus, plugging 0 in, 1 over x sub m. Now, we said that it was going down and to the left, but I got a plus sign right here, but don't worry about that. That's easily figured out because this number right here is larger than this number right here. I'm looking at the entire fraction. This fraction is larger than that fraction, so when you do subtract, you'll end up with a negative number. You can leave it in the long complex form right here, where you can get a common denominator. It depends upon the math training that you've had. Minus 0, we can do better than that. So I hat k lambda y sub m over x sub m square root y m squared plus x m squared plus j hat k lambda. Now it comes down to how do you want to actually do it. Do please be aware or cautious that your lambdas and x's do not look the same. I've made that, come close to making that mistake several times. I think I had to correct myself at least once, but it could have been in a different video. And so xm minus the square root of ym squared plus xm squared over x sub m square root of y sub m squared plus x sub m squared, getting the common denominator. Some people will balk at that one because it got a radical under the in the denominator. I don't care. It's good enough for physics. I know the math people really don't like radicals in the bottom, and well, we each have our own things that we stress over. It's not one of the things I'm stressing over, or it's not one of those things over which I am stressing. And there it is. It is not pretty, but it is doable. So now I'm not going to work through it, but at least set it up. If I have a line of charge like this, then I can break this up into two problems here. And I now have, if I treat it like that problem right there for one half, and then I can go down here for the other half, and then just add them together. Just please be aware of adding directions, or I don't necessarily have to add the two pieces like that. I could just change my limits of integration to get this exact same result. And don't forget, and I don't mention this in enough videos, but rejoice. This is physics.